This plot is from a recently published paper on velocity curves. But velocity curves of what, do you think? Well, since you know it's going to be something astronomical, you might rightly guess that those are rotation curves of stars within galaxies. Many galaxies have what is referred to as a flat rotation curve. As you move away from the center, the speed of the stars going around the center rapidly increases, but then that speed quickly levels out and becomes flat. For example, let's look at a beautiful galaxy called NGC 4527. How do we establish the rotational velocities of the stars in this galaxy, and why do we care? I think it's instructive to see the data that we actually collect when we want to know how galaxies rotate. And we'll look at data from the Nobeyama Radio Observatory in Japan, which is a delightful collection of various radio telescopes. Here's a picture of the grounds. The data I will show comes from the group of the dishes on the upper left of the photo. Now, in the image below of the data collected, the lower right is an optical image from the Sloan Digital Sky Survey. The lower left is the corresponding radio image from Nobeyama. And the money shot for how a galaxy is rotating is at the upper left. So this is how we calculate the rotational velocities of various parts of a galaxy. The upper left image is only the light emitted from the energetic hydrogen atom, the famous 656 line. The wavelength of that light is 656 nanometers long. On that upper left insert, the horizontal axis is where we are along the long axis of the galaxy. The center of the galaxy is in the center of the insert. The vertical axis, though, of that upper left plot is frequency. If there were no movement within the galaxy, all the dark signal there from the H656 line would all be at the same level, just a straight line across the image. But it's obvious that it's not all at the same vertical position. That is, not all the hydrogen 656 line is coming to us as 656 nanometers long. Most of the light has been either red-shifted or blue-shifted according to the movement of the atoms relative to us. The stars on the left side have their 656 line shifted to longer wavelengths, meaning they are moving away from us. The stars in the right side of the galaxy clearly have their 656 line shifted to shorter wavelengths, indicating that they are moving towards us. From the center of the galaxy, the speeds increase in a steep straight line. That is, as you move away from the center, the velocity of the hydrogen increases rapidly. But then, very quickly, it levels off to a constant velocity. This is a shape of velocities which many galaxies have, yet it is not what you would expect from Newtonian dynamics, as long as you assume that our telescopes are seeing all the matter in the galaxy. I still do not understand why any scientist would assume our telescopes show us all the matter in a galaxy. But with that assumption, there's not enough matter in the galaxy to create these rotation curves, hence the urge to propose something like dark matter. Now, in 1933, when Zwicky proposed dark matter, he just meant ordinary matter that we could not yet see, hence dark. That's reasonable. It was decades later when the theorists started inventing all kinds of very strange properties for this dark matter. This is not an essay about dark matter. I will only say that the hubris and the myopic vision of the astrophysical community on this topic is astounding. To assume that only gravity controls the cosmos, and to assume that our existing instruments could possibly measure all the matter that lies so many trillion miles away, and then to invent a new category of matter, whose properties are shamelessly chosen to be just all those properties needed to prop up the gravity-only model. On top of that, to use funding threats and career threats to silence any other points of view. Wow! A thoroughly embarrassing chapter in the history of science. You know, if your previous model of the universe did such a bad job at explaining things, and that clearly had no effect on your humility, then why should I trust your new model? I'm sure that many of you know that galaxy formation and rotation can be explained with electric current flow, which you can read in this paper. It is also important to know that you can explain the galactic rotation curves by simply assuming our telescopes observe only 1/10 of the ordinary matter present in the galaxy. To summarize then, we calculate the rotation curves of galaxies by looking at how atomic lines are shifted. Many galaxies have what is called a flat rotation curve, which most astrophysicists claim is evidence for dark matter, which can never be seen. Alternatively, the known physics of twisted Birkeland currents predict rotation curves. Getting back on track, what is this first plot that I showed? It is not the rotation curve of a single galaxy. It is the rotation curve of whole strands of galaxies. Galaxies are concentrated along gigantic filaments that span the entire universe. There are thousands of little specks in these strands, and each speck is a galaxy. And those filaments made up of those galaxies rotate. I usually don't even look at artist impressions of these things, but this one here is okay at showing the filament of galaxies leading to a cluster of galaxies. The problem with this representation is that the galaxies in the red and blue filament, they're way too big. Actual galaxies would be much smaller on this scale. They would just be tiny little dots inside the filaments. We have gathered enough data about the details of the rotation of filaments made up of galaxies to see that in many cases the rotation curve of the filament is also one of these flat rotation curves. Supergalactic filaments are predicted if you assume that electricity plays a role in the cosmos. Galaxies on rotating filaments, that is not. I repeat, it was not expected with the previous gravity-only model. Since our telescopes now show us the filaments everywhere, the well-funded institutions have rewritten all their computer models, tweaked or added adjustable parameters, added magnetic fields where input was needed, and of course, they've added dark matter, sprinkled in only where it is needed, and voila! University cosmology is back in business, claiming to predict the large-scale structure of the universe. Then someone comes along and suggests that, electricity might play a part in all this. And Occam comes sweeping in. Get that electricity out of here. We don't need that arbitrary complication. The authorities have it under control. We just need to tweak a few parameters, like maybe the primordial power spectrum, which is how much structure your region starts with before you even hit run on the computer. Well, you need a little more resulting structure. Let's just increase that parameter a tad. And then there's the initial angular momentum distribution. If the previous computer run led to too much rotation in the filaments of the galaxies, well, just back off that initial parameter a bit. Well, then there's the baryonic physics, such as the density threshold for star formation. Might need to push that parameter up a bit to get some more stars earlier on. And then there's the friction coupling constant for neutral versus ionic particles. They have to radiate away some of that pesky angular momentum as heat. And maybe we noticed that once the computer filaments started to form, then they spun apart when the clumps came too close. Okay, that's no problem. Bring down the supernova energy coupling efficiency parameter, and let's just make the momentum transfer timescale a little bit longer to reduce those pesky blowing apart. Oh, and since we're dealing with filaments composed of galaxies, we need to assign an average outflow angle for the active galactic nuclear jets, and the orientation distribution, let's make that random, because we all know the universe is random. And we got to set the timescales for their formation and the distribution fractions for thermal versus momentum transfer and the turbulence spectrum. Maybe we should go with a multi-exponent model for the turbulence spectrum. And then, of course, the solving of the equations, well, we might find that a fourth-order Runge-Kutta converges for the high densities, but we need a fifth-order Runge-Kutta for a convergence of the outer, lower filament densities. I think you get the point. I probably listed only about a quarter of the adjustable knobs that must be set at the beginning or even modified during the simulation itself. Yippee! Years ago, I started down the road of computer simulations for gravitational systems. And when I started to see what was really going on under the hood, I knew in my gut that I would be very unhappy going that route. But wait, if you assume electricity is flowing through the supergalactic filaments, then the flat rotation curve, the shape of it, is already predicted. Of course, there's much that needs to be flushed out, but the very start of the electrical model already predicts the overall morphology, and the whole thing is fractal. The giant cosmic filaments carry current, which causes them to rotate and have the flat rotation curve. Those currents then split into filaments, which form galaxies. And those galaxies rotate in a similar fashion, but on a much smaller scale. The filaments break into filaments, and they all rotate with the same general fashion. Now, as for some computational details, I'm working on a subsequent episode for how we can actually apply the EU models to all this and get numbers for current flow and magnetic field strength, temperature and pressure, etc. So stay tuned.